Hey, let's take a look at what we are doing today. We load a bunch of data from the sources, whether they are near real time data sets or whether they are batch data sets, into our one lake. So, if you want a real quick uh, briefing around data engineering or one lake or other things, I will tag an additional video I have recorded for data engineering workloads. Please go through that. But for today's session, we'll assume the data is in one lake and we use Fabric's data science experience to generate a machine learning model. In order to generate a machine learning model, we need a cleaner data set, and we perform something called future engineering to engineer all the features that are needed for the machine learning model. We also use the inbuilt capabilities both in Python as well as Spark machine learning library of how to actually train, experiment with various models. We'll explore auto machine learning future, and once the model is ready, we will actually predict, we will make the batch predictions and load the predictions for future use for the downstream systems. So the idea of this session is just go through the data science experience. So let's just start with a journey of how a typical data scientist um, start their journey in Fabric, and we will see the end-to-end process. Uh, so as usual, we will just go log into our powerbi.com. Once we log into the powerbi.com, you go all the way, you go all the way to the bottom left corner. You will see various options here. For today's experience, we'll be choosing data science option. So let's go ahead and choose the data science option. You have various artifacts, various modes here to generate various artifacts. So let's start with notebook experience. So the moment you click notebook, you can create a notebook just like that. And every notebook comes with a default environment, and the default environment and the default Spark pool. So the advantage of using the workspace default Spark pool is it takes literally like 8 to probably 12 seconds to spin. At least that was my experience. So that you don't need to wait like a full 3 to 4 minutes for the Spark compute to be ready. But if you want to create your own Spark pool, you can, and you can associate your own environments. You can do experimentation with PySpark, Scala, Spark SQL, Spark R. We'll see, like many experiences. Today, I won't be touching Scala or R, but mostly PySpark and Spark SQL. That way, if needed, I will do a separate video or other things. So you can attach a lake house, which is part of one lake right from here. You can actually choose the existing lake or a new lake house. For today's purpose, I will always be choosing the analytics dev um, lake house. And once you add the lake house, um, then that's it. You can just start coding, right? So my raw data sets are within fraud data folder. Today, what we'll be doing is we will be loading three different files that corresponds to a fraud data set. We will get the account information, comma separated file, a fraud transactions comma separated file, and untagged transactions comma separated file. So we need to perform future engineering with these three different files, and then create a machine learning model that detects fraud. So let's start our journey here. So as usual, I made notebooks because it is already, and I'll go through them because it's really tough to code live. Um, so let's actually go to our workspaces, analytics dev. So as usual, we'll filter here, right? On the right hand side, we'll go and filter. We'll filter on notebooks, experiments, environments, models. So we will sort everything by type. So today I will be starting my journey with fraud detection future engineering. So future engineering is nothing but you need to actually convert all the input data sets into a meaningful format wherein you create the data set in such a way that um, you actually have x variables and y. X variables are the variables that influence y. So in this case, the machine learning model is the fraud model, and whether fraud occurred or not is what we are looking for. It's a classification model. So a bunch of x's, we train bunch of x's with known y's, uh, and then we given a new x and we get a new y, right? That's the machine learning. So like I said, we have three different files. An account information file, as you can see here. Account information file contains all the information about the account ID, and when a transaction occurred, what is a snapshot of that particular account, because account holder could change the addresses, or like they could actually perform transactions from different zip codes. So whatever might be, this is a snapshot of like any account level changes when a transaction happened. Then we save whatever we have read into a permanent table, um, uh, uh, in our lake house. In this case, don't worry about bronze, silver, gold. I am not actually demonstrating multiple layers of lake house today. I will store everything in the bronze layer just for simplicity. I assume that in real life you will be actually putting them in various places, but today I just put everything in the bronze layer. So I save every file that I read in as a table within my lakehouse bronze. So I have pretty much three files. I have account info file, fraud transactions file. So fraud transaction files are nothing but um, we tag all the transactions, or some system tags all the transactions that they are fraud, right? So this particular file contains the transaction ID, account ID, and very basic information about uh, the fraud transaction itself. So then there are again bunch of transactions which are like the running transactions for the account. And if a transaction is the fraud, what we do is we actually take the fraud transactions that are available in fraud transactions file, and we actually take the minimum and maximum date for those transactions, and then we actually sweep through untagged transactions and tag those transactions that happened in untagged transactions as fraud, and remaining we tag them as non-fraud. The reason we need to go to untagged transactions is there might be actually like a third party system or other system or application in your organization uh, that tags all the fraud transactions. So what untagged transaction has is much more detailed, right? So you need to enrich all the informations corresponding to the fraud transactions, because you see there are a bunch of information here that says where the transaction occurred, which country it has originated, what is the method of the payment, what is the instrument used, etc., etc. There is lots of information here, right? That is gold for machine learning. So the ability for us to synthesize all of this information is called future engineering. So let's see the future engineering. The first and common thing all the machine learning practitioners face is cleaning up the dates. And now don't get surprised. We will be doing everything in SQL. The reason I am showing that is this is a SQL developer can get very productive and perform the machine learning in Microsoft Fabric space. As you can see, you know, if you know SQL very well, you can pretty much write any logic in order to clean the code. For example, here for me, in order to format all the dates, I create a table and I am formatting all the dates because the dates are not clean. In this case, you know, the time portion of the dates is not good, and therefore I am cleaning. I'm not going through each and every logic of this, but you know, for those of you who know SQL, you actually know really well how to actually accomplish this. Um, then you know what we do is we take all the untagged transactions and we'll merge them with our account information table. And when we are merging with our account information table, we actually see in the account info table there are the account snapshot is have uh, a given interval. So what we need to do is when we join the untagged transactions with the account information table, um, we take the account information that is relevant when we are really looking at the transaction. So let's say there are three transactions in the untagged transaction, and the first transaction, you know, the customer was staying in address A. We pick up address A of the account. It's account level information. And let's say for the next two transactions, customer for whatever reason, let's say they moved the country and they updated the address, will be taking the new account level address. These are all the account level attributes we'll be taking when the transaction has occurred. And as you can see, right, this is the logic. And again, if you're a SQL developer, you understand that you can do, you know, like any advanced analytic functions such as rank, or you know, you name it, in order to do this. Then once the information is merged, we will actually get the account level attributes populated on the transactions. And then all that is left for us is we need to tag uh, all the fraud transactions. So for example, let's say your third party system tagged a transaction and it sent the information to us, right? Um, so all it has is the fraud transaction. But what we do is, just because a transaction is not there in this table doesn't mean that fraud has not occurred, right? So we will compute something called the fraud occurrence time period in the fraud transactions table, wherein we take the minimum date and the maximum date of the transaction per account, and we will sweep that start date and end date across the untagged transactions to make sure we pick up all the transactions, so that, you know, better safe than sorry, right? So all the transactions that occur during the time period, we have confidence on this system, because this system picks up the transactions when they started and when they finished. But that does not necessarily mean all of the transactions are tagged. So we take the minimum start and minimum end date from this table, and then we look into previous account merge table, right? The account information on all transactions. And then we actually pick up all the fraud transactions and tag them, all unfraud transactions and tag them. And the tagging process again is, you know, like the logic is here. If you're a SQL developer, it's not tough to follow this logic at all. So the label 0 means fraud has not occurred. Label 1 means the fraud has occurred on these transactions. Label 2 is they are outside the boundary. Yes, fraud occurred, but they are outside the boundary, which is not of interest to us. So we don't care about those. We'll filter them out. Okay. And then we have to compute all of the things called risk attributes. So the risk attributes are, you know, like take any attribute within you know, like um for the transactions, take any attribute. For example, take the attribute called local hour when fraud has occurred, or like the transaction currency code where the transaction has occurred, and look at the odds. Look at the odds in such a way that against all the remaining values, right? Against all the remaining values, um, how many, like for example, let's say label zeros. How many label zeros and how many label ones are occurring, for example, let's say during 11 o'clock in the night, right? And you compute something called odds. So odds are nothing but um, how much fraud has occurred over how much fraud that has not occurred during that particular time period. And now expand it to everything else. For a particular currency code, um, what are the odds that a transaction occurred against all the odds? So you extrapolate all of that information. And in general, all this says is the metadata, how much of a metadata is contributing to the odds of occurrence of fraud, right? So that's all we are saying. So this is called future engineering. Okay, so this is the 101 of future engineering, where you take data, which is our gold, and you dig the nuggets out of that data, right? And then finally, what we also have to look is, we also have to look if a fraud transaction has occurred, let's say in a given time period, what are the number of other transactions that occurred during the same period? And if so, what is the total amount of the transactions? All of this is also future engineering, right? So we are actually engineering the new futures from the existing futures and computing, let's say, usually how much this user um, how many transactions that this user makes in a given day, this user makes in a given 30 days, and if so, what is the purchase of those transactions, right? So all of that information will compute. Now we will append everything and create a fraud final table. And fraud final table, for example, in order to look at the fraud final table, look, it's very easy. So we'll go to we'll go to fraud final, and then we will say load data. This also gives you an idea of how much time it takes to start a, see, the session started in 4 seconds. So that's one of the advantages of um, using the default pools, right? We spoke about that. So let's see what it does. Spark job is running. Okay, sure enough, it gave us. As you can see, look how many futures I engineered. I engineered all the risks corresponding to that and other things, right? So now the data set is in a shape that we can perform machine learning, which are X and Y values. We have all the X's in form of the futures that we engineered, and our Y is the label, right? We can use any classification algorithm to classify this. So let's move on to the next notebook that shows you how to do the data science or model creation. Yeah, let's see this notebook of how we do the data science. As you can see here, some of the key libraries that we are loading: MLflow. MLflow, it's a open source machine learning library, wherein like it tracks all the metrics and whatnot in a standardized format. So I'll be using MLflow, and I'll show you actually what's the significance. Then I'm using the regular scikit-learn library, and wherever you see synapse.ml, this is the Spark machine learning libraries equivalent of Microsoft, right? So whatever Microsoft has to offer, for example, the auto machine learning within Microsoft machine learning library is synapse.ml.automl, right? So this is, think of it as equivalent to um, the regular Spark machine learning library. Okay, so this is a classification exercise, so I need bunch of classifiers. So logistic regression, random forest, and one of the gradient boosted trees, right? So I have all of my data in fraud final. Then I actually convert the types into float. Some of them are, float 64. So I just want to convert them so that, it'll be easy on AutoML. So for AutoML, in order to prepare the data, um, all I need is numbers, right? I don't need objects. So I really don't need, account ID, transaction ID, and transaction date time, because these three already, in future engineering, um, I all eked out all the information from these three things, and IDs themselves are of no significance. I need the label, and of course, as you can see, all of these account level information are still as like strings. See all of these strings. So machine learning doesn't recognize strings, right? So I need to convert them into some kind of a number, and you can do various pre-processing steps, such as one hot encoding is one of the popular way to bucketize these things. So I take only the information I need. I'll exclude, like other information such as account ID and whatnot. And there is this library called get dummies within pandas. Get dummies creates the dummy variables, right? So for example, dummy variables is nothing but, like if you have, let's say, three types of cards: Visa card, MasterCard, and American Express card, right, as instrument. So what it does is, it'll say, instead of saying this particular row has Visa card, it will instead say, if Visa card is not present, then mark as 0. If it is present, then mark as 1, right? Something like that. So that also means you'll be creating a lot of, uh, columns in order to house. So it is a highly denormalized table. So it does that. So we see actually something called correlation. So mm, usually, I am a big proponent of computing everything as a graph, so that you can see which attributes in this, um, for example, which attributes are highly correlated, right? So label is correlated to itself, therefore it is one. But after that, you have bunch of, I think I need to clean this up. I should not have label string here. So there can be a positive correlation or negative correlation. If they are highly negatively correlated or highly positively correlated, we are interested in those, right? So we are interested in these, we are interested in these, right? So because they positively or negatively are contributing to the signal, right? So then, um, I actually get all the algorithms. I thought of using, like light GBM also. So if you actually, want to do automated machine learning, you tell automated machine learning what are all the models that you want to train, and then you tell, you say what the target column is. In our case, it is label, and you tell it, right? So okay, you need to actually yeah, take into consideration all these different um, algorithms when training, right? So every model needs hyperparameters. So the hyperparameters can be any, like sometimes for tree based algorithms, it will be, like what should be the depth, what should be the number of the trees, and like what would be, like the different bins. Um, so for light GBM to reduce the variance, um, you will try different bagging fractions as shown here. So give all your hyperparameters, right, that are needed. Then what we do is we search the space. We search the space, um, which is parameter space that we are giving here. And then we actually, Okay, so by the way, I want to say something. So this particular data set, fraud transactions are very less. Like, if fraud transactions are 1,000, non-fraud transactions are 199,000, which is very common, right? Fraud is not, um, a common occurrence. So the classes 0 and 1 are highly imbalanced. So in order to take care of that, you have to do something called smoting. And in order to do smoting, I am using this imbalance library. And also, like, I am installing it here. If you don't want to install it every time, you can create your own environment that you can tell that, okay, this comes pre-installed. So once I do the smote, I say that, like, increase the ones from 1,000 to 20,000, right? Like so, and leave the zeros as they are. So once I do that, you have to actually split the data set into training and testing, and then you tune hyperparameters, you evaluate accuracy. You don't need this, as there are many metrics. Okay, so accuracy is just one of that, and I'm choosing that. And then you ask auto machine learning what is the best, right? Then it ran for 8 minutes and 41 seconds. uh, and then it gave me the best model, as you can see here. And it gives me, like, what is the accuracy of the model, what is the precision of the model. It's good, right? So it is actually doing, it did a good job. And also I can plot the confusion matrix, right? True positives versus true negatives, true positives, true negatives, false positives, false negatives. And then, I can evaluate the predictions. I can evaluate the predictions. I can actually take these two predictions, and, like, it's all good. Like, the data is looking good. So can you do all of this without using auto machine learning? Yes, right? So you can actually use any of the Spark libraries, and you can actually, like, see here, you can futurize, and you can actually do the exact same thing. For example, I tried with some random algorithm, right? I don't care, I'm just showing you the light GBM classifier. I'm saying it has the um, unbalanced data set as an input, and I trained the model. And, even I can see the future importance, right? So which future is contributing to the fraud, right? So what are the top futures that are contributing to my fraud? um, so obviously it looks like, the billing postal code, the local hour has a significance. So where the IP address is originating from also, like, yeah, these are the things that we know intuitively. But this made up data also is made up in such a way that, like, we get the same results, I guess. And then you can do the predictions by doing model.transform, and once you do that, you get the prediction. Then what you can do is, you can pretty much take these predictions, again redo whatever I said, right? So um, yeah, that's it. Like, you can do pretty much the same thing without AutoML. But usually I like to use AutoML just to zero down on the hyperparameters I might be using and the model that AutoML suggested. And then I can pick up the model from there, and I like to actually, like, do further last mile adjustments to that, to make it proper. So this is as simple as this, right? And as you can see, I did not actually, like, do any huge Spark adjustments. This is the power of the as service, as you can see. And all the experiments are automatically tracked, which is one of the beauties here, right? So you can actually go here, see the experiments, um, see the source of the notebook, uh, you know what are the different metrics. Then you can see the different run parameters, right? um, yeah, so you can actually track everything to the T, and it will also store all of your models, right? This is the Sorry. AutoML best model. This is the experiment. Yeah, and let's see. Fraud model. So the best model you can store and see how many versions this has. And you can also store the input schemas and the output schemas corresponding to that. And um, it nicely maintains the version. It'll capture the requirements.txt, the Python environment used. And it pickles the model. Okay, so it does all of these things. So with that said, next I will show you how to use ml flow in order to track, right? So okay, let's go ahead and see. You don't need to use Spark. You can as well do everything using scikit-learn. So like I'm showing here, all the steps are exactly the same. But this time I'm using pandas data frame. I use like train test split. So light GBM classifier, and the fit. This is just the Pythonic way of doing stuff, right? You really don't need Spark to do that. And if you're a Python person, you can achieve the same level of efficiency. That's the point of showing this, the exact same thing that we have done, right? And I want to show you, like I promised, about the ML flow. In the ML flow, like you can infer the signature. So what signature is nothing but like what is the structure of XS, and what is the structure, what will it return, right? What is the Y, and what is the model that is used to do that. So ML flow you can use like this, and you can say ML flow slide GBM has log model. This model will be logged, and then like you can save also the metrics corresponding to that, right? So this is the run name, and that is the experiment. So if you go to this particular thing, what you see is, we captured the run metrics, we captured the input schema, we captured the output schema, right? So in a sense, right, we are memorializing how we did, right? Which data set we used, what is its structure, and what is the model, right? And what is a model, what is a model's version. In this case, the model is fraud model, and it's version 1. You can associate to that experiment this model again has the exact same things I have shown to you, right? And we memorialized everything, the data set used for that model, as well as the version of the model itself. So in the future, if one of these changes, you might need to do retraining, right? um, so that simple it is. But if you really want to actually explore further into how you can actually adjust your own settings, the easiest way that you can do, provided you have access, is go to your workspace. In the workspace, go to workspace settings. Within data science and engineering, there is Spark settings, and in the Spark settings you can create the pools, you can associate the pools. And also there is this thing called high concurrency mode, wherein multiple notebooks can share the same Spark application. So in that case, right, you really don't need to the Spark session. You need to wait like 7 seconds, 12 seconds to get the Spark session, but you can actually reshare. That's good thing. And then see, the automatically track machine learning experiments and models when turned on. That's why it was tracking, like even when I was not using ML flow. You can give your own Spark properties, right? And also, one thing I want to touch before that is, you can create your own environments. So if you go actually like to the main workspace, within that workspace you can say new. In the new, you will see environment. Okay, that's the environment. So that environments you can create, and mm, for example, if you go here, you can see all the public libraries, like you can you can customize your own libraries so that you don't need to remember the imbalance library I have been using. I can very well like just get that library from PyPy and install it, so that time and again I don't need to go to notebook and redo that stuff, right? It's really pain to do that. Likewise, you can get your own custom libraries. You can upload the wheel files and whatnot, right? And also some of the computes that you could associate with this environment, right? Like so. And you can also define Spark properties, right? um, for everything. So anyways, so with that, I think this is a good place to stop coding, and I wish you all good health and wealth. Okay, talk to you all very soon. Bye.